What I would like to say something about, maybe we should turn off the, yes, concerns various concepts in modern physics which are of great importance. In fact, most of them occupy center stage at this period of the history of physics. But so we'll start with the vector potential. When Maxwell wrote down the Maxwell's equations in about 140 or 50 years ago, he wrote them in this form. J is the current, and B is the magnetic induction, and H is the magnetic field, etc., etc. This A, B, C, D, E, F, G, H labeling was the original Maxwell form. He wrote all equations in component form, so he had 20-some equations. He repeatedly emphasized the importance of vectors and tensors, but somehow he did not write his equations in those more condensed forms, which is what I had just shown you. When he got his bachelor's degree, he wrote to Lord Kelvin, who was very precocious, 7 years Maxwell's senior, who was already a full professor. He said, Maxwell said he wanted to work in electricity, and asked Kelvin, Lord Kelvin, at that time Thomson, to give him some references. And the literature does not show today what was the letter with which Kelvin answered Maxwell's request, but we can guess that that probably included a paper of 1851 by Kelvin, in which Kelvin used the vector potential to express the magnetic field. Then within the next 10 years or so, Maxwell wrote these 3 papers. The first one on Faraday's lines of force, second one on physical lines of force, the third one a dynamical theory of the electromagnetic field. These 3 papers were the papers that founded Maxwell's equations. Some approximately 10 years later, he wrote a book, a treatise on electricity and magnetism, which sort of summarized these ideas in the first 3 papers. Now, usually today, when people talk about Maxwell's equations, there's a tendency to refer to the 3rd paper and the treatise on electricity and magnetism. But actually, the most important concepts are all already in papers 1 and 2. Roughly, we might say that the intellectual heritage that descended on Maxwell followed somewhat these lines. In Great Britain, there was Faraday, a superb experimental physicist who found one of the key laws of electromagnetism, one of the 4 key laws of electromagnetism, perhaps in some sense also the most sophisticated one of the 4. And Thomson, that I just referred to, and Green and Stokes were theorists who preceded Maxwell in various areas, including electricity and magnetism, and hydrodynamics, and so on and so forth. And Maxwell had borrowed the ideas from all 3 of these theorists. On the continent, Ampere, Neumann, Weber, and Gauss had tried to perfect a theory of action at a distance for electric and magnetic interactions. And it is this tradition in Great Britain, especially due to Faraday's physical concepts that launched Maxwell into the fundamental idea of a field, and not an action at a distance description of electromagnetism. That is of profound influence. I'm sure everyone in this audience knows field theory is the theory of all branches of theoretical physics today. And when you hear about this very exciting developments about strings, it is really just an attempt to further generalize the concept of the field. Now, when Maxwell started, some of the later Maxwell's equations have already been written into differential equation form, including Ampere's law. This is Gauss' law. But the Faraday's law was still in words. Faraday wrote many papers. Faraday was not a mathematician. He had very little training in mathematics, so you could not find a single equation in Faraday's papers. And naturally, Faraday's law, which was realized to be very important already at that time, was not written in mathematical form and into differential equation form, and that was the aim that Maxwell set for himself. He wanted to write these physical ideas of the field of Faraday into differential equations. Now, the particular point of Faraday, the particular concept of Faraday that Maxwell wanted to put into mathematical form was this concept called electrotonic state. This repeatedly occurred in Faraday's papers, but it was never very clearly defined. It was very descriptive, and that was the problem that Maxwell had to struggle with, how to capture the essence of Faraday's ideas. That he captured that very well, and that he even later, in some sense, talked about the future developments and generalizations of it. I'll come back to at the end of my talk. In Maxwell's first paper, he tried to invent a mathematical quantity which would correspond, in his opinion, to Faraday's idea of the electrotonic state. And for example, in his treatise, written some 10 years later, he said the conception of such a quantity on the changes of which, and not on its absolute magnitude, the induction current depends, occurred to Faraday at an early stage of his researches. And that quantity turns out to be the vector potential. In part 2 of the paper, of paper 1, there is the title for the whole part on Faraday's electrotonic state. And the essence of that part, in fact, the essence of that whole first paper was the statement that the electrotonic intensity or electrotonic state of Faraday's is equal to the vector potential, which had already been introduced by Kelvin in the paper of 1851. Now, it was very obvious that Maxwell realized this was an important step, and he was afraid that Kelvin might think that Maxwell was stepping on his toes. So he was very careful to summarize at the end of paper 1 about what is it that he did and what is it that was done before in this paragraph. With respect to the history of the present theory, I may state that the recognition of certain mathematical functions as expressing the electrotonic state of Faraday and the use of them in determining electrodynamic potentials and electromotive forces is, as far as I'm aware, original. That means that's his idea. But the distinct conception of the possibility of the mathematical expression arose in my mind from the perusal of Professor Thomson's papers. What he's referring to was the fact that Thomson had written down the equation H is equal to curl of A, which defined A. And in fact, Thomson had discussed in great detail the flexibility, the non-absolute definition of this H equal to curl of A. And Maxwell here had made very clear what was it that was his contribution and what was it that was Faraday's contribution. The second important contribution, according to Faraday himself, occurred of Maxwell, occurred in his second paper, and that was the introduction of the displacement current. The displacement current was introduced in part 3 of the second paper. In those days, it was customary to publish a long paper in several parts, occurring at different times of the same journal. And so indeed, in March and May 1861, he published the first 2 parts, and then in 62, he published the part 3. And in part 3, he introduced the famous displacement current. It was introduced as proposition 14 to correct the equation 9 of part 1 of electric currents for the effect due to the elasticity of the medium. And this is where, for the first time, Maxwell launched into the displacement current. Now, I read that paper several times, and I know there are many people who have tried that. I think it's safe to say that nobody understood how Maxwell was trying to figure out this displacement current, because the paper was full of diagrams like this, which is a network of vortices. What Maxwell was trying to do was the following. In paper 1, he suggested that the vector potential, or the electrotonic state, is the vector potential whose curl is the magnetic field. But then at the end of the paper, he said that this is too mathematical. That was not his words, but that was the meaning of his words. This is too mathematical, and we have to have a mechanical model to illustrate this. So in the second paper, he began to create a mathematical model in which he would have some quantity equal to the curl of some other quantity. And you can see that, you can easily understand that in order to do that, he would have a lot of vortices. So this is a honeycomb network of vortices. Each of these circles is a vortex. It's a very complicated thing. And through arguments which I cannot follow, which I maintain nobody today can follow, he began to write paper 2, and then in the midst of it, he suddenly realizes that something is not quite right, so he added a displacement current. Now today we have a tendency to teach our students how the displacement current came about. We would say that if you don't have the displacement current, Ampere's equation does not conserve charge. But that was a consequence of the paper 3. After Maxwell introduced the displacement current, it was not what led to the displacement current. So the usual explanation of the introduction of the displacement current was logically a correct one, but historically not a correct one. But anyway, once he launched into the displacement current, the fundamental ideas of Maxwell's equations were already there. Maxwell's equations were not understood by physicists. There was great controversy about what Maxwell's equations meant, and there were great controversies also about whether they agree with experiments. In those years, in the latter part of the 19th century, many people made their names by contributing to that. In particular, Lorentz's greatest contribution really was in understanding Maxwell's equations and applying it to various electric and optical phenomena, and demonstrate that those agreed with experimental results. Then around the turn of the century, there appeared new forms of Maxwell's equations which went by the name of Maxwell's equations in the Heaviside-Hertz form. Heaviside was a genius. He was an electric engineer, not very much learned in physics, but he had the great intuition and very penetrating intuition. Hertz was a great experimental and theoretical physicist. The two of them independently found that Maxwell's equations are too complicated. They don't need to be that complicated, and in particular, they eliminated the vector potential. The Maxwell's equations that I showed you earlier had the vector potential A all over the place, but they found that they can be eliminated. The vector potential can be eliminated, so that you only have the electric and magnetic field, namely D, H, and E. There's no more the vector potential in it, and that is the state of affairs well into this century. In fact, when I was a graduate student, I was taught that the only thing which are meaningful for electromagnetism are the electric and magnetic fields. This was, in some sense, drilled into all students of physics, and it's still been drilled into many students of physics in graduate schools all over the world today. Now, Heaviside was a very colorful figure too, and he was very, very happy about the elimination of the vector potential. I shall not show you the passages in which he referred to the vector potential as garbage. But I'll show you Whittaker's statement about it. Whittaker wrote a foreword to one of Heaviside's books, and in which he said, the great service which Heaviside now rendered to science was to clear away this accumulation of rubbish. And what he referred to as rubbish was the vector potential. Now, conceptually, a very important thing you can already find in Maxwell. Maxwell found that the vector potential A was a momentum. How do we know this? There was a one-sentence description which was not very clear, but he named the vector potential in some places as electromagnetic momentum. He sometimes called them electrotonic intensity, sometimes called them three quantities, F, G, and H, because that's how Kelvin before him called the three components of the vector potential A. But in many places he called A the electromagnetic momentum. So therefore it's clear that he realized that it is an electromagnetic momentum. Now today, this expression P, which is the momentum, minus E over Ca, is an expression which is a most important expression. When you have a particle moving which has no electromagnetic charge, you write a momentum. And if that particle is endowed with a charge, all you have to do is you replace the P by P minus E over Ca. So this P minus E over Ca today is something of cardinal importance. I spent a little bit of time last year trying to trace who did this first. Now, this was certainly popularized, if I may use such a term, by Dirac. When Dirac in 1928 in writing down his Dirac equation, in showing that that gave rise to a magnetic moment. That was a stunning achievement. What he did was he first wrote down the Dirac equation without charge. Then he replaced the P in it by this expression, and lo and behold, there dropped out of this consideration the magnetic moment of the electron. So therefore, I think all the people of my generation learned this replacement through that paper of Dirac's. But when I look back before Dirac, because Dirac did not give a reference to why he did this. When I tried to study this, I found that nobody took credit for it, because it was something which was not entirely that useful, and before Dirac, and also there are some questions about it due to the fact that the vector potential is well known to be not completely well defined. You can add a gradient to it, and it still serves the purpose of making H equal to curl of A correct. So people did not make claims about it for at least 30 years before 1928. It was sort of floating around in some of the papers in various forms. But today, of course, we know the fundamental meaning of this. Now, Maxwell's equations in the 20th century exerted not only great influence because it agrees with experiment, but also because it gave rise to a conceptual structure of theoretical physics. And both of these are related to symmetry. One is the symmetry of Maxwell's equations, which are called the Lorentz symmetry, which was really first pointed out by Einstein. The history was something like this. The mathematical expression for the transformations that left Maxwell's equations unchanged was due to Lorentz. But Lorentz did not understand the meaning of it. And it was Einstein who pointed out the meaning of it. There's a misspelling here. The second symmetry of Maxwell's equations, which was pointed out through the years 1918 to the year 1929, was due to Hermann Weyl. And we'll come to that now. Hermann Weyl introduced the gauge invariance in 1918. He wrote 3 papers in the year 1918, the most important of which was this paper, Gravitation and Electricity, which was now collected in his collected works, volume 2. What was his motivation? Well, in 1950, that was 5 years before he died, he wrote an article about, it's called 50 Years from Planck's Work. In this is a review paper. In this paper, he talked about his 1918 paper. In 1950, the gauge field concept was not yet accepted as very important. In fact, it was not accepted as important at all. It was something, the then atmosphere I could describe to you in the following way. I was a graduate student in the late 40s, and we have all learned about the gauge invariance or gauge symmetry. But it was not particularly useful. And the only use that we put it to was something like this. If there is a theory seminar, at the end of the seminar, if you ask, is your result the gauge invariant? People would know that you are very smart. And if the speaker happened not to have checked the gauge invariance, he would be even more impressed by your acuity. But in 1950, Hermann Weyl evidently regarded this paper of his as very important. He was very much attached to it. And so in this review paper of 1950, he described how he got onto this idea. And he said that after 1916, when Einstein published his general relativity paper, many mathematicians got extremely interested. So they were talking about parallel displacement, and that included Levi-Civita, included Weyl himself, and another mathematician whose name I think is Hesburg. Does that ring a bell? Hessenberg also. Anyway, people talked about the parallel displacement. So in 1950, Weyl said, if you have a vector, if when you transport it by parallel displacement, when it comes back to the original position, it may not have the same original direction. Warum nicht auch seine Länge? Why not also its length? Why couldn't its length also change? So therefore he built a theory of parallel gauging. And that's the origin of the word gauge. When you move around the curve, you want the length to continuously change. As I said, Weyl was very attached to this idea. Weyl submitted his paper to the Berlin Academy, and the editors went to Einstein and wanted Einstein to comment. Einstein looked at it and wrote a comment, which was published as a postscript to the Weyl paper. The comment was a very perceptive one. Einstein said that if he said Weyl was very ingenious, but if Weyl's idea was correct, if you have 2 meter sticks at the same point A, and you bring 1 meter stick to the point B in space-time along one path, and bring the other meter stick to the point B in space-time along another path, by the time that they reached B, since their histories are different, their gauging would be different, they would not necessarily have the same length. So that means that if you standardize 2 meter sticks, then later on they may not have the same length anymore. And if that is the case, the whole of physics would disappear. It was a devastating argument, but fortunately the editors did not reject the Weyl's paper. They published Weyl's paper, but they showed Weyl before the publication Einstein's objection. So Weyl wrote a postscript, which was also published. And I read the postscript several times. It's philosophical. It essentially says, no, Einstein misunderstood what I mean by length changing. But he did not explain what is it that he meant. So I think it's correct to say that he was greatly bothered by Einstein's objection. And in fact, in the subsequent years, he tried to talk his way out of it, mostly in philosophical terms. But then quantum mechanics was developed independently of all these gauge ideas. And after quantum mechanics was developed, it turned out, and was pointed out by Fock and by London independently, that Weyl's idea was essentially right, only you have to insert an I. It's not a gauge factor like this, where in Weyl this constant is real, and you have length changes, but you have an I in there, which is a phase change. And once that is done, the theory becomes not only the correct idea, it becomes necessarily the right idea when you have quantum mechanics. In other words, quantum mechanics and electricity and magnetism amalgamated together, you have to have this I, which is very similar to Weyl, only there is a I inserted into his gauge factor. Weyer accepted this, so in 1929 he rewrote his paper, this time with I in it. But the name gauge has already taken hold, so we still call it the gauge field. Actually, it should have been called a phase field. In 1972, 10 years before Dirac died, he said, so if one asks what is the main feature of quantum mechanics, I feel inclined now to say that it is not non-commutative algebra. That was what everybody thought in the late 20s. It is the existence of probability amplitudes which underlie all atomic processes. Indeed, if you look at today's important areas of physics, you find all these phenomena: superconductivity, superfluidity, Josephson tunneling, Aharonov-Bohm effect, flux quantization, vortex quantization, holography, lasers. All of these are deeply related to the concept of phase, are deeply related to the insertion of that I in the gauge field. Now, as I said, when I was a graduate student, all the theory graduate students know about the gauge transformations, but it was not necessarily very essential. It was not that useful. So I thought maybe we should generalize it. Instead of having a phase which is just a complex number, why not make it a complex number with the absolute value 1? Why not make it an element of a Lie group? So I tried that, and the generalization of A mu would become a B mu, and the B mu would become a 2 by 2 matrix instead of a 1 by 1 number. But the next step is I have to define the electromagnetic, or the generalization of the electromagnetic field. Today we know that that is the right generalization, and this expression is I think is known to the mathematicians since the 1930s, or if not 30s, certainly the 40s. But I didn't know it, so I didn't have this. I just wrote on this. And if you write on this, if you ask for the transformation of F mu nu under a transformation on the B, it becomes horribly complicated. So that idea, which I had as a graduate student, didn't work. But as time went on, the necessity of doing something like this became more and more apparent, because experimental physicists were discovering more and more particles. And the question was, how do these particles interact? And since electromagnetism was really the only one whose interaction is well known by some fundamental principles, so perhaps the way out of that fix is to have another more generalized principle for which you can write down interactions. So I returned to this several times, but each time I got stuck. Until 1954, when I was visiting Brook, and my office mate was Bob Mills, now at Ohio State, and together we looked at this again and said, how about we add a quadratic term and a cubic term and so on and so forth, and maybe that would eliminate some of these complications of the transformation. And by the time we got to the quadratic term, we found that that's enough. You don't need any cubic or quartic terms. So we wrote this paper. So that was the origin of my paper with Mills of 1954. Then I moved to Stony Brook in the 60s. And one day in the late 60s, more or less at the time of the Stony Brook Anti-War Fund organization, I was teaching relativity. And I wrote down this equation for the Riemann tensor. And suddenly I realized that this is, in fact, very similar to this equation. And then I sat down and identified the coefficients. And if you identify the coefficients correctly, it's the same. It's exactly the same equation. only if you have to identify this BB with this Christopher symbol in the correct way. So I know that there's something going on here. So I went to Jim Simons, who was the department chairman, and Jim looked at it, and he said, this is connections on fiber bundles. So that's the first time I heard the name connection and the name fiber bundles. So I said, where can I read up about the connections on fiber bundles? He said, read Steenrod. Now, I knew Steenrod because I bought his house in Princeton. In 1955, my wife and I were looking for a house, and a real estate agent said that there's a house on Carter Road for sale. It turned out it was by a famous mathematician, Steenrod, who was trying to sell it, so we bought the house. And I found that Steenrod didn't like to talk. If you ask him a 3-sentence question, he would answer in 2 words. Then I launched on his book and found the book has the same characteristics. So I didn't understand. Struggling with it for a while, I did not understand what the fiber bundle was all about. In fact, that's the origin of a joke of mine, which was quoted in the literature. I said that the modern mathematical books are very difficult to read. There are essentially only 2 kinds. The first type, you cannot read beyond the first page. The second kind, you cannot read beyond the first sentence. But anyway, I couldn't understand what this is all about. But then there were other physicists who were more knowledgeable in mathematics, who started also to write about fiber bundles and so on and so forth. So therefore, in the mid-70s, I went to Jim again and said, I've got to learn fiber bundles. So I convinced him he should give us some luncheon lectures. And I think he must have given us 6 or 7 of those, something like 2 hours for each lunch. And we learned various concepts about modern differential geometry and modern topology, elementary notions, but they were very useful for me. And then I suddenly realized that what we were talking about gauge fields, both the non-abelian version, which is the electromagnetism, and the abelian, both of the abelian version, which is the electromagnetism, and the non-abelian version, were in fact all connections on fiber bundles, and that the definition of a fiber bundle and the definition of a gauge transformation, which was always local, the way that we understood it, has a global connotation which one has to explore. And after understanding that, TTU, who was and still is at Harvard, and I wrote a paper explaining what we really did was we borrowed what we learned from mathematics and rewrote the gauge field concept into languages that the physicists could understand. Now, in the process of that, we thought that it would be good to have a dictionary. So we wrote a little dictionary. What we call, for example, gauge potential, which is a generalization of the electromagnetic potential, is connecting a principal fiber bundle, and so on and so forth. Electromagnetism without magnetic monopole is connection like trivial U1 bundle, and Dirac's monopole quantization is the classification of U1 bundle according to the first Chern class. So I and my colleagues at ITP in the Stony Brook were very grateful to Jim. And at the end of that, we decided we should give him a present. So we went to some of his friends and asked if we want to give Jim a present, what would be good? And the suggestion was he couldn't spell, we should give him a dictionary. So we gave him a dictionary. Now, the connections on, oh, sorry, I forgot something. There's a fundamental concept in physics, and that in fact is one of the Maxwell's equations. It's the divergence of F mu nu. And that, physics-wise, is called the source. It's the electric charge density and the electric current density. And that is of fundamental importance, because that's the source of the electromagnetic field. So I went to Jim and said, what do you call it in mathematics? And he said that we don't deal with such a quantity. So that's why there's a question mark in this paper. Then Singer was visiting half a year later, and I explained to him this table, and apparently he got extremely interested, and he went to Great Britain and collaborated with Atiyah, and they pointed out that if this is zero, that this quantity is extremely interesting. If it is zero, you would have solutions which is of what is now known as self-dual or self-anti-dual gauge field, and the Atiyah-Singer theorem is tailor-made to tell how many different solutions that self-dual or self-anti-dual field could have. And apparently because of their prestige in mathematics, this news propagated among the mathematicians and became a very active field of research for many mathematicians after that. Now I want to make a very important remark about revisiting Einstein's objection. Einstein said that if you bring two meter sticks back to the same point, they would have different. This is now in 3 dimensions. They would have different lengths if Weier's theory were correct. But nobody bothered after 1929, after I was inserted into the concept. So let us look at this concept again, this question of Einstein's again. And then we will find that these 2 meter sticks, when they come back to the same point, would not have the same phase, but they would have still the same length. As a consequence, Einstein's original objection does not obtain, because you can still standardize the length of the 2 meter sticks. However, you can ask a follow-up question. If these 2 meter sticks no longer have the same phase, no longer have the same length, but they do not have the same phase, could you measure this phase? Now, to measure a phase difference of 2 things, you need an interference experiment. So you would need to do these 2 meter sticks. After they come back, you do an interference. Now, interference experiments are very commonplace, but not with meter sticks. With electrons, at least not yet with meter sticks. The miraculous thing is that people can now do it with atoms, but not yet with meter sticks. However, you can do them with electrons. And that, in fact, was an experiment proposed by Aharonov and Bohm in 1959. I remember when that was proposed, many people were deeply opposed to it. They said that their experiment in detail is the following. You have 2 electrons, one following this path, one following this path, going back to the same place in 3 dimensions. And you have a solenoid here so that there's a flux inside. But you do it such that there is no leakage of flux. So there's no electric field outside of that solenoid, no magnetic field. And Aharonov and Bohm said that they would interfere here. And that met with a violent objection, because people say that if the electron in neither path sees any electric field or magnetic field, then they cannot have any, they cannot be influenced by what's inside of the solenoid. So this was a very bold proposer. That was claimed to have been proven experimentally by Chambers, but the Chambers experiment was very inaccurate, so it generated more confusion than confirmation of the idea. It was only in 1986 that Tonomura in Japan finally had an accurate experiment which showed that the Aharonov-Bohm experiment was valid. Bohm is now dead, but Aharonov last year received the Wolf Prize for this contribution. Now, the way that the vector potential enters into field theory today is because of this expression where P replaces the minus IH bar delta, the differential operator, a la quantum mechanics. A, the definition of A has a certain flexibility because of the fact that I've already referred to the fact that if you add a gradient to A, it does not change the equation H equal to curl of A. How does that flexibility in A get into an expression like this, which cannot be that flexible? Well, the answer is that the gradient operator operating on something with a phase would create something which absorbs that flexibility. So this is now the way that the connection physically enters into field theory. And that, of course, is well understood by the mathematicians when they think of the covariant differentiation. So this is a highly geometrical concept from the mathematician's viewpoint. From the physicist's viewpoint, we first had this, we had this, and then we put them together, and eventually we realized that the two is one thing. Is that the end of the road? Most of the theoretical physicists do not believe so. There are probably additional complicated geometrical manifestations or geometrical complexifications which we have not yet launched into. Especially because the gauge field relation with gravity in quantum mechanics is meeting with still difficulties. Now, reflecting on this long history, let me remind you that you write down this wonderfully simple equation. This equation is called Stokes' law in physics. Perhaps it's also called Stokes' law in mathematics. How did that get into physics? Let me read you a paragraph, 2 paragraphs from Maxwell. As I proceeded with the study of Faraday, I perceived that his method of conceiving the phenomena was also a mathematical one, though not exhibited in the conventional form of mathematical symbols. What he really means was that it's not the differential equations. When I had translated what I considered to be Faraday's idea into a mathematical form, I found that in general, the results of the two methods coincided. So that the same laws of action deduced by both methods, so that the same laws of action deduced by both methods, but that Faraday's method resembled those in which we begin with the whole and arrive at the parts by analysis, while the ordinary mathematical methods was founded on the principle of beginning with the parts and building up the whole by synthesis. In other words, Faraday had words which were integral in concept. And by the Stokes' law, Maxwell converted that into a differential equation. That's this relationship between the global and the local one via Stokes' law was recognized by Maxwell himself as the essence of how he got to Maxwell's equations. After Faraday died, Maxwell wrote a very moving obituary, and the following 2 paragraphs was from that obituary. The way in which Faraday made use of his idea of lines of force in coordinating the phenomena of magnetoelectric induction shows him to have been in reality a mathematician of a very high order, one from whom the mathematicians of the future may derive usable and fertile methods. From the straight line of Euclid to the lines of force of Faraday, this has been the character of the ideas by which science has been advanced, and by the free use of dynamical as well as geometrical ideas, we may hope for further advance. Thank you.
Sometimes there was a paper by Klein, 39. Sometimes is
Felix Klein?
Oscar Klein.
Oscar Klein.
Which is sometimes claimed to be a precursor of Young-Mills equation. Any comment?
Yes. In 1938, Oscar Klein, who is not related to Felix Klein, Oscar Klein was a very distinguished physicist who played an essential role in many aspects of the founding of quantum mechanics. In 1938, there was a conference in Warsaw at which he presented a paper. The paper was not noticed very much, and it was only about maybe 10 or 15 years ago that somebody somehow found this paper. And in that, what Oscar Klein was trying to do was to write down some couplings. And people found that those couplings have a great resemblance to the gauge field couplings that Mills and I wrote down. Mills and I, because of this quadratic expression of B nu commutator, showed that the couplings would have non-linear expressions, and these nonlinear expressions were almost the same as what was in Klein's paper. But Klein did not have the concept of gauge transformation. So as a consequence, his paper was forgotten about. Nobody paid very much of notice to it. And Klein himself, as far as anybody has found, did not refer to it and did not further develop it after the Second World War. So as a consequence, it remained unknown until I think it was the early 80s when it was rediscovered. But I think the key point was that there was the reason for the disappearance of the paper in some sense was because there is no concept of gauge transformation.
There's more to the story. Klein brought the paper to Einstein, and they had a 2-year conversation about it before Einstein would let him even think about publishing it. And Einstein said in the end, well, yeah, it's all very nice, but it's a technical trick. It doesn't really go anywhere, but I'll let you publish it. So he really put him down for it. Similar to the kind of letters that were sent between Einstein and Cartan, which I think have been inefficiently looked at because Cartan's idea of putting torsion in the connection and using generalized theory in the next century, I think, will probably be shown to be what we really need, and to make things quantizable. What I wanted to say, a comment, which is that Maxwell proved many, many things, and we seem to only know him from Maxwell's equations. He proved mathematically, using Hill's equations, that Saturn's rings were unstable and should have literally thousands of rings, before we found that with space probes. He has a paper called Hills and Dales, where he actually gives a rising water proof of the Morse inequalities, long before Morse. And somebody asked him towards the very end of his career what his greatest discovery was. And his comment was, that's very simple, Michael Faraday.
I'll make two comments. One is about Maxwell's other contributions. He also was the first one, I believe, who wrote a very interesting paper about the importance of the transformation properties of vectors and tensors.
Right.
And in fact, the terms divergence, curve were all originating from that paper.
And I'd like to add two more comments. Grassmann's work with differential forms predates the British obsession with tensors and vectors that were given over by Maxwell. But Maxwell thought that putting things in differential form would be too much for electrical engineers. So in his own private diary, he thought that really things belonged in Clifford algebras. And it turns out that in the end, people in Britain took a compromise, and they were teaching to people in the before 1900 something called the quaternionic form of Maxwell's equations, which has some slight resemblance to SU2 gauge theory, actually, even though electromagnetism is really a U1 gauge theory. There was a lot of stuff there. People were very reluctant to take the full power of Clifford algebra and put it into, the hands of physicists and engineers. And if they had, we might have been maybe 75 years ahead of where we are now.
I have a second remark. That's I'll get from you later, perhaps, this correspondence or this exchange between Oscar Klein and Einstein. I've never heard of it.
My actual source for this was a NPR television program where they interviewed the son of Oscar Klein.
The son of...
oh, that's Kaluza.
That's Kaluza.
the son of Kaluza.
Oh, okay, so this is a different paper. But it's called Kaluza-Klein theory, right?
Yeah, but it's different time.
Different time.
Oh, no.
Okay,
Kaluza-Klein... I guess Kaluza is well known to the mathematicians?
I don't think so.
Oh, Kaluza-Klein had written a paper in which they started from a 5-dimensional theory, right, and tried to reduce it to a 4-dimensional theory.
That I guess is different.
And that has something to do with Oscar Klein's paper. Oscar Klein tried to copy that idea. Indeed, people who are doing string theory is also copying that, because they are reducing things from the 11 dimension or 10 dimensions,
right,
down to 4.
Really pushed down by Einstein.
Right. Thank you.
One further historical comment. Stokes got his name attached to Stokes' theorem because he said it as a problem in
right,
a Tripos exam. I don't know who told him about it.
Green, in a letter.
Yes.
It's on the cover of Spivak's Calculus of Manifolds.
And Maxwell took that exam. So Maxwell well...